Next, we have Joseph Meany speaking. He is a materials scientist from Atlanta, Georgia, who received his PhD in chemistry from the University of Alabama in 2016 and continues to work in various science communication venues with a focus on how chemistry and nanotechnology impact society. He is a member and contributor to the TVIW and the Tau Zero Foundation, promoting the development of new materials to solve challenges facing humans in Earth and space. His first book with co-author Les Johnson, Graphene, the super strong, super thin, and super versatile material that will revolutionize the world, was released in February 2018 by Prometheus Books. Please welcome Joseph.
Thank you, everybody, and thank you all for your attention. So today I'm going to be talking about metamaterial-enhanced graphene as a beamed energy sail for interstellar probes. Now, I've had the fortune of being preceded by many scientists, Les and Artur and Greg Matloff, that have gone over much of the motivation and history behind light sails. So I'm actually getting the opportunity to skip ahead on those portions a little bit, and we'll refer back to those for the history and motivation. So I'm going to jump mostly right into the proposal behind this design of the metamaterial enhanced graphene for the photonic sail. To go over it very quickly, we're looking to maintain a very low mass or very low areal density and a thin material so that we can achieve high accelerations. We would want a high reflectivity over a wide bandwidth to make the most of as many photons as possible, whether coming from the sun or coming from a specific laser. We'll also want high tensile strength. That's important because the g-forces that a sail will undergo, especially with very fast acceleration from the beamed energy, is going to affect the stability of the sail. We'll also want high thermal stability. High thermal stability is important so that the sail itself doesn't melt either on a close approach to a sun or doesn't break down under high laser powers. Now, the Breakthrough Starshot, which I summarize here, put out a paper in 2018 which summarized a lot of the aspects that they wanted to focus on with respect to a laser beam sail, but many of the other requirements that come from a solar sail as well hold. So I'm going to go into a little bit of the graphene fundamentals for those of you that are not material scientists and are scratching your head about what graphene actually is. Graphene is one of the allotropes of carbon. You may be familiar with diamond or carbon nanotubes as other examples of allotropes of carbon. Here I have an illustration of the allotrope graphite, which is made up of many sheets together of graphene itself. So if you take a pencil lead and strip it away with some sticky tape, as Novoselov and Geim did in 2004, you get yourself a single sheet of this isolated graphene. And so graphene is known for having a very lightweight areal density, for having a very high tensile strength and a very thin thickness. It is also generating a good deal of excitement for its electrical conductivity and its flexibility. However, as you see toward the bottom of the graph here, the graphene itself is actually very, very low in absorbance and very low in its reflectance as well. And so others in the past have used graphene or proposed graphene as a solar sail material, but as Artur said in his talk earlier, graphene itself actually does not make sense as a photonic sail material because of its high transmission through the monolayer. However, here I have proposed, based on literature precedent, a metamaterial based off of nano-sized prisms that would be deposited on the top of a graphene surface so that you get the strength and flexibility and lightweight aspects of the graphene, whereas then you're also getting the optical properties of the metamaterial. So here I've pulled a quote from the paper that outlines the important optical properties with over 5.9 reflectivity in the near IR, with 10 to the negative 5 absorbance based on this silicon nanotube, silicon dioxide nanoprism on a graphene-based substrate. The metamaterial is made from 450 wide by 450 nanometer long by 450 nanometer tall cubes with about 220 nanometers of space in between the cubes. So it is this repeating lattice structure on a surface that achieves such a high reflectivity in the bandwidth. And so there we go. Non-continuous materials actually have a very long history within the literature. So metamaterials happen to be this exciting new capability of non-continuous materials inside the literature, going all the way back to Jeff Landis's 1977 proposal. A lot of these non-continuous materials, though, use the trade-off of reflectivity to just simply shed the mass. In the case here with the metamaterial, the shed in mass of the non-continuous material is also giving you a gain in the reflectivity. So you're actually optimizing both of the parameters without having to lose any kind of performance. So here I have a quick outline of some parameters about the metamaterial on a surface, given the areal density of graphene there at 7 times 10 to the negative 7 kilograms per meter squared. You have a thickness of the graphene that is 0.3 nanometers. So to stress this graphene is monoatomically thick. So it is, the thickness of the graphene sheet is only limited to the actual thickness of the carbon atoms that make up the lattice. We have a density of the silicon, the prism dimensions below that. And based on that, I calculated there a fill ratio, which allows us to get the total area density of the graphene itself. So you see a fill ratio there of about 0.45. So you can use that to back calculate, based on some of the properties of the silicon dioxide, about what kind of areal densities you can achieve using this metamaterial surface. And so the top line of the chart here gives you the areal density of a 450 nanometer thick continuous plane of silicon dioxide, excuse me, which is sitting there at about 1 gram per square meter, which roughly matches what some of the benchmarks were being discussed in the previous lectures about solar sails. But it gets even better, because we're not using a continuous plane of silicon. We're shedding a lot of those extra atoms that are not actually benefiting our performance. And so when you take the adjusted areal density of the carbon I'm sorry, the metamaterial surface itself, you get down to about 0.5 milligram per square meter of the sail. Then if you add back in the graphene surface there in the row below that, the graphene surface is, for a 450 nanometer thick cube, essentially negligible. Your substrate itself is actually not contributing much more than 1% or 2% to the weight. As a bit of completeness, the metamaterials themselves don't necessarily need to be designed as these 450 nanometer cubes. We could also discuss the opportunity for optimizing parameters by decreasing the thickness of that layer of metamaterial. And so I have the calculations that show that we could get down to 1/10 of a gram per square meter if we use an exceedingly thin metamaterial surface on top of the graphene, getting down to 4.5 nanometers. Now 4.5 nanometers, that's about 30 or so atoms thick. So we're talking about very, very thin layers of these silicon dioxide metamaterials on the surfaces of the on the graphene. So the total weight of a 10 nanometer, I'm sorry, total mass of a 10 nanometer metamaterial-enhanced graphene sail are there for your perusal, getting down to still within the milligram and fractions of a milligram weight. So this gives us really solid hope that we can use it for a metamaterial solar sail or photonic sail. Now, the same literature article which analyzed the silicon dioxide nanocubes also provided some spectroscopic data based on their manufacture. And so what we have here is a chart that I've called out where over the course of a 1 to 1.2 lambda change based on the Doppler shift of an accelerated sail to 0.2 c, you can see that across the top of the chart, you maintain better than 99% reflectivity in this material over the 1 to 1.2 bandpass range that you would need for a specific laser-propelled sail. The dotted line down at the bottom is the absorbance, and you can see that all across that line, we're still hovering about 10 to the minus fifth fractional absorbance in this particular metamaterial as well. So this gives us good hope that not only are we going to give ourselves a lightweight sail, we're going to get one that has the high probability of surviving large laser fluxes if necessary. Graphene itself has a melting temperature of about 4,500 K. So the transfer of the heat phonons from the silicon dioxide to the graphene substrate can actually be used as an emissive layer as thermal modulation. So that gives us further proof of principle that we would want to analyze this kind of material. So back on the other slide, when I was discussing the mass of a total sail, I gave two different options. The mass of a total sail using a single layer of graphene and the mass of a sail that uses bilayer graphene. And bilayer graphene I felt was interesting to investigate because also in 2018, a paper was released that showed that bilayer graphene, if you hit it with a sharp force, the electron orbitals of the planar graphene sheets actually deform into one another, and those graphene orbitals start to dehybridize as the delocalized sp2 electrons orbitals, which are important for the strength of the graphene single plane, and they start to rehybridize into sp3 hybridized orbitals, which are a lot closer in function to that of diamond. So it basically boils down to that if you have a sharp force applied to this bilayer graphene construction, perhaps a interstellar dust or micrometeorite, this sharp force would create temporary diamond-like bonding within these graphene layers to help resist some of the damage that would otherwise be applied to a single layer of graphene, and much more so than polyimides or the mylar films that we have available as the state of the art. As a comparison to contemporary materials, we kind of want to get down to brass tacks. How is this going to help any of our missions? Why would we even care to look at this? Yeah, great, we're getting a bit of reflectivity. Yeah, great, we're saving on mass. But if we take a look at this, we have a aluminized mylar film is 12 micron thick, whereas the graphene film itself is 4 orders of magnitude smaller than that. And so for the same sail area, you can actually pack that sail into a much tighter space. And even if you're adding on the 200, 400 nanometers, you're still a couple of orders of magnitude thinner than this aluminized mylar film. So you're still getting considerable volume savings. Now, the tensile strength of the aluminized mylar is there at about 186 megapascals. But the graphene itself, due to these strong carbon-carbon bonds within the single plane of the graphene, is 3 orders of magnitude stronger than the contemporary polymer films. So by shedding the weight, we are actually making the sail much, much stronger. This isn't an incremental step. This is completely in the next ballpark. And then, again, comparison apples to apples. The total area density of the mylar film is the tens of grams per square meter, and we're actually getting a 2 orders of magnitude benefit with the thickest of the modeled metamaterial graphene films. So there's definitely a lot of promise here, especially in the optimization realm. So to bring it all around, low mass and high reflectivity are going to get us to the stars fast. The low absorbance means that we have a stable sail that can accept high photon loading. The high tensile strength and toughness means that it can accept high accelerations, and high thermal stabilities and low acceleration distances make this an extremely promising material to begin to investigate. There are plenty of open questions. I'm not going to go over these one by one. But how reliant is the metamaterials z-axis height important to its overall reflectivity? Are we going to kill it by making it thinner? What can we do to optimize the geometry of that structure? Instead of using photolithography or other reductive manufacturing techniques, is there some way that we can improve the scalability of manufacturing a large area graphene sail by using self-assembly? That's extremely important for the cost of a sail. And how wide of a bandwidth can we get with greater than 99% reflectivity if we're going to, in fact, use solar photon flux rather than a laser photon flux? There's also considerable engineering questions open. Front and foremost, how are we going to make graphene that is this large in area? The current state of the art sits where graphene is only able to be made on a couple of square millimeters. There is a huge push to try to make large area graphene sheets for all sorts of applications, but we're just not there yet. I was quoted as saying in an article a year or so ago that if we figure out how to make a square inch of graphene, it might as well be a square mile of graphene. That's basically where we are at this point, and whoever cracks that nut open is going to be a very famous, very rich person. So with that, I'd like to thank Les Johnson and Sandy Montgomery for really pushing me to present here to you all this afternoon. Dr. Matloff and Rhonda Stevenson for a lot of their excellent conversations going through all this. TVIW, Tau Zero Foundation, and Prometheus Books for publishing our 2018 novel here, Graphene. So with that, I'd like to open it up for any questions.
I assume that these sails would have to fly into space folded up, so there's also a requirement to fold up and then deploy. Can this kind of material have that capability?
It can, but I would actually push back on that notion that while, yes, the first graphene sheets that'll be manufactured in large area will be here on Earth, if we're talking about the size of the graphene sheets that are going to be deployed, we're going to want to manufacture them in space so that you're not limited by that requirement. But the toughness of the graphene sheets are going to allow them to survive liftoff. And you know, when you have a strength that is over 1,000 times that of the currently in use Mylar and Kapton films, they have, I imagine they would have a very high survivability rate.
Hey, Joe. Right here. So real quick, two questions. One, what is a cubic prism? And the second one is for 100 gigawatts power across a 1 meter sail, you only need 1 kilopascal of strength. So why do we need all this additional tensile strength in the system? Thank you.
So for the first question, the cubic prism is just a way that I was describing a cube, but then opened it up to the non-cube prisms, non-cube three-dimensional structures. When you vary the z-axis, they're, of course, no longer going to be cubic. So I was using that to transition from the cubes themselves into square prisms. So I should probably update square prisms rather than cubic prisms in future versions of this talk. And then the strength aspect, more is better. You're getting it for free because you're not having to engineer it into the film itself. This is a property that is inherent to the graphene. And one thing that you could consider is that the bonding between the silicon dioxide and the graphene monolayer is going to create some electron density loss between the carbon atoms themselves in the graphene lattice, because then you're going to have electron density going toward the silicon dioxide. So the monolayer will lose a bit of strength, and one of the first open questions to answer is how much strength loss is there in a monolayer graphene when bonded to the silicon dioxide because of this interaction between the C and SiO2 layer. If we happened to need that strength, then that's where the bilayer graphene comes in. And so the low areal density of this second monolayer that would be the load-bearing structure sort of comes back to it. Yeah.
So we've seen in the previous talks that our light is not going to be incident normal all the time, as we're going to be changing directions. So that 99.99% reflectivity was at incident normal. Do we know how that reflectivity is going to change by changing your angular dependence as you hit your surface?
Right, and something that I did not perfectly address in the talk is that this metamaterial is actually a diffuse reflector, not a specular reflector. So that there is going to be some non-normal distribution of the photons reflecting off of the surface. Now, this would be very interesting for optical modelers, especially Jacob, to figure out, oh, hey, so we're no longer working with specular reflectance models. What does the diffuse reflectance do for beam riding stability in these different models of irradiation with the laser photons?
So how are the two materials going to be bonded together? I mean, is that like another layer that's going to add to the weight, or a layer that's going to have to be radiation resistant and flexible, and et cetera?
No, I expect that there are actually going to be covalent interactions between the SiO2 layer and the graphene itself, and that's why when I was addressing Grover, right, that we'd have to look at this exact interaction between the two layers. Graphene and SiO2 are, have been made together in the past. So I don't expect that there's going to be considerable delamination, because if you talk about folding and unfolding from deployment, you're going to get some kind of delamination of those structures. But that can be experimentally determined on small scale here on Earth inside the laboratory. That would be a relatively rapid and inexpensive test to do. And in fact, density functional theory calculations can do a lot to really explain the behavior of the interaction at the interface between the carbon and silicon dioxide layers.
One of the properties that metamaterials seem to have is that they tend to concentrate electric fields spatially. Have you looked into how this will affect the maximum power you can have on the sail, especially for laser propulsion?
I've not. That's a really interesting point, and I think graphene's capabilities as a very high electrical conductor, I'd be interested to see exactly what doping the metamaterial does to the electrical properties of monolayer graphene itself, and then find out what that does between monolayer and bilayer graphene growth. The van der Waals forces between the two layers of graphene itself are actually kind of weak. It's non-negligible. You can put two wires onto a pencil and conduct electricity just fine. But the conduction out of plane is several orders of magnitude lower than the conduction within the plane of the graphene. So that definitely opens up another area for some really exciting fundamental science questions.
Yeah. Actually, I just was sort of triggered by that statement that you said that the reflectivity is not specular, that you're getting diffuse reflection. That's going to be really hard to produce on a metamaterial. I'd like to see the analysis on that.
Sure, I can forward
yeah.
the paper on that.
Yeah, please do. That'll be very much change a lot of the analysis of stability, among other things. It's all the stability analysis has assumed either specular or directed reflectivity. I'm not sure how you can get that unless you put a random spacing between the elements, which would give you a specular component.
Yeah, absolutely.
So, interesting.